let's continue our session, and it's my pleasure to introduce the next speaker, Dmitri Talalaev, and you can see the title of the slide. So please.
Thank you very much. It's a great pleasure. Yeah. I think it's the best way to use such places, like to organize the scientific one. The title of my talk is rather ambitious. So it is a category of braided sets and higher tangles. So the principal hero of my talk is the Yang-Baxter equation. And it is important in topology due to its role in quantum invariance of links, nodes, and related structures. But it has different applications in mathematics, in algebra, in integrable systems, and quantum integrable systems. So it's an interesting object, and the problem of its classification of solutions of Yang-Baxter equation is rather important. What I'd like to propose in my talk is to think about solution of Yang-Baxter equation like an object of a category, and to state some natural question in this category. So the question of morphisms between such objects, the problem of extensions of solutions of Yang-Baxter equation. So principally, it's a way to construct complicated solutions for Yang-Baxter equations, starting from the simple ones. And so it's rather treatable for the moment. I'd like to explain you some concrete results and different projects which are related with the program of categorizing of the solutions of the Yang-Baxter equation. But the main new idea of this talk is a way to generalize this concept to the high dimension. So just to say what is the extension of the solutions of the tetrahedron equation. This is an equation which is the high dimension generalization of the Yang-Baxter equation, and it takes important role in topology in classifying dimension of something. Yeah, I don't, but it's a one dimension plus. So in topology, it is related with the problem of classifying the two nodes in four space. Okay, so here is just the list of some words which are related to my talk. Okay, not important. And some result of my talk was done in joint works with Валерий Бардаков, Игорь Карипанов, Маргарита Преображенская, and Georgy Sharygin. So I'd like to start with the well-known object, a solution of the Yang-Baxter equation, and the set X on which this solution is defined. So this X I will call the Yang-Baxter set. And it's good to say what is the morphism of such object. So F is a map from set X to set Y. And it is a morphism of Yang-Baxter set if we have with this commutative diagonal. There is a very closely related object. It is a braided relation, and S is a solution of this braided relation if this equation fulfills. And to each solution of the Yang-Baxter equation, we can associate such a solution. I don't see. So there is a procedure to come from the first equation to another equation using just the transposition operation in the Cartesian product of set X. This algebraic structure is related with another interesting algebraic structure, which is a quandle. And a set X is said to be a quandle if there is a binary operation A star B with satisfying this list of axioms. For example, if we have a group, we can associate a group quandle with it, which has set G as a set, and the operation is defined in the first example, just by applying the operation of conjugation in the group. And for example, it's a very familiar example of a quandle is Alexander quandle. Alexander quandle, which is defined like this, and it is related to the construction of Alexander polynomial. There is another algebraic structure related with the Yang-Baxter sets, which is called the skew brace. And it is a set with two operations, dot and circle, such that both operations are groups, and these operations are related by this condition. There is a very important example of such structure. If we have a group G with exact factorization, which means that it can be represented, each element of this group can be represented as a product of elements of subgroups. It's not a direct product of groups, but it is a group with factorization. Then we can define the operation G circle H, which is G1, H, G2. There, G1 and G2 are the parts of the factorization. And it is a theorem that two such operations produce a structure of the skew brace. Как убрать? So what is written? What is written here? What is written here? It is a statement that such a circle operation is the same as the product of the direct product of groups with the opposite operation on the second. And it is important because it appeared in the literature on quantum integrable systems as the tracing transformation.
Well.
Thank you. Okay, so it is a such operation, and it has very rich history in integrable systems. Okay, if we have a skew brace, we can define a map lambda by this formula. Then we can define a map from the Cartesian product of G, Cartesian square of G to itself by this formula. And the statement says that this map solves the Yang-Baxter equation. So it's how these structures are related: the structure of the skew brace and the structure of the Yang-Baxter set or the braided set. Here I just present you an example of such structure for the group of exact decomposition. Okay, so I defined object and morphism of my category of braided sets, and there are some examples of the extension of such object. And the first one is produced by the relation of groups and braided set. Let me recall that a set with binary operation star with this property is called the self-distributive set. And if X is a self-distributive set, then the map explained here is a braided is a map solving the braid relation. So the set X is a braided set in this case. Let K be a group with multiplication AB, and let us consider the extension of just the extension of. Normally, it is characterized by a homomorphism from the group K to the group of UTA automorphisms of G, and moreover by classes of second homologies of the group K with the coefficients on in the center of the group G. Let us consider the case there. This group is just a set. As a set, it is a direct product of sets G and K, and express this operation, the group operation, and the associated distributive operation on the set by this formula. There is a version of the Yang-Baxter equation, which is called the parametric Yang-Baxter equation, which is given by this formula with some parameters in expression for the map R. So the set, a theorem says that if you started from an extension of groups with commutative K, such a map solves parametric Yang-Baxter equation. So it's an example of extension of groups which produce an extension of braided sets, and moreover, it gives an example of parametric Yang-Baxter. Okay. Let's go further. There is another example of extension of braided set, which is defined by the categorical construction. So there is a theory of Yang-Baxter complex, which is related with each solution for the Yang-Baxter equation. It is a little bit tricky, so I'd like to define by the formulas what is the two categorical of the Yang-Baxter set, or corresponding to the solution of the Yang-Baxter equation. So let us start with three variables x, y, z, and produce another set of variables x1, x2, y2, z2, etc. And the same set of variables with upper indices. So a definition of the two cycle for the Yang-Baxter complex. So it's a function on two variables in X with values in some field with the condition of such type in the core of definition. And there is a theorem. If R is a solution of the set-theoretical Yang-Baxter equation and phi is a two cycle defined by this formula, we can construct vector solution for the Yang-Baxter equation by the following procedure. We associate a vector space to the set X, just taking the basis element for V corresponding to elements of X. And we define a linear operator A acting on V tensor power 2, specifying its values on basis vectors by this formula. So the statement says that this is a solution of the Yang-Baxter equation, and I'd like to interpret this solution as a solution on the product of the initial set X, just the Cartesian product of the initial set X with the vector space V. So in a sense, it is also an extension given by class of second homologies associated to the solution of the Yang-Baxter equation. So very analogous to the theory of group extension. Another result, another recent result obtained with Valery Burdakov, who's here. Let's consider a Hopf algebra over a commutative ring K. It is almost commutative if its co-multiplication satisfies such a solution, such a condition. There is a construction of product of Hopf algebras. Let B and C be Hopf algebras with co-multiplications for unities, antipodes, and R matrices. So the almost co-commutative Hopf algebras. Two such algebras, and let R be an element of C tensor B, which satisfies such condition. Then the tensor product of B and C can be endowed with the Hopf algebra structure with the multiplication, the tensor product, just the tensor product multiplication, but the co-multiplication is not trivial. So it is it is deformed with the help of the additional element R. The antipode and conunit also defined in this context. The theorem of Valery Burdakov and myself says that under the condition of the previous construction, the Hopf algebras B and C for quasi-triangular Hopf algebras B and C, the co-multiplication is also quasi-commutative and quasi-triangular. And it means that it produces new solution for the Yang-Baxter. And this solution is given by the beautiful R at the end of this statement. This construction is related with the theory of representations of virtual pure braid group, but it will be expressed in details during the talk of Valery Burdakov. So my goal here to say something about the way of generalization, this concept of extensions of solution of Yang-Baxter equation to the higher dimension, to the situation of homological tetrahedron. And I'd like to recall what is in 2-knot and why and how this homological equation appears in this book. So a 2-knot is an isotopic class of embedding of the two-dimensional sphere to R4. A class of non-trivial examples of 2-knots is given by the Siemens twisted spoon knot, which is a generalization of the Artin spoon knot. It is obtained by rotating the long knot with simultaneous rotating of this long knot in its own space. Generally, one works with 2 knots with the help of diagrams. And a diagram of a 2-knot is a singular surface in R3 with singularities of most general types. So it is admitted to have an arc of double points, a triple point, and a Whitney point. Okay, so one works with the information of this graph of singular points of the diagram. And there is a Rosman theorem which explains, which is an analog of the theorem of Rademacher about Rademacher moves. So there is a list of seven moves like this, and the 7th one here. And the theorem of Rosman says that 2 diagrams represent equivalent knotted surfaces if and only if one can be transformed from another by a finite series of moves from the list above and an isotopy of a diagram in R3. There is a standard way to construct invariance of two nodes. Due to Quarter-Site and their colleagues, which is principally an analog of the quantum invariance in the theory of one nodes. So one can consider a coloring of two leaves of a diagram with an elements of a quantum, satisfying such conditions. Here is the definition of the Zika cycle of a quantum, and here is the theorem of Carter and colleagues, which says that such a partition function, which is a product of which is sum of the colorings of products over triple points of some functions on triple points, it is invariant of a two-node. But there is another way to think about two nodes. From my point of view, it is more integrable. So it's an expression which is more familiar in theory of integrable statistical models as the vertex representation of a model, and it is related with different algebraic structure, which is the mallogic of tetrahedron equation. It is expressed by this equation of the fourth power on a linear operator in the tensor triple product of the space V, and it is expressed by such diagram, which illustrates some move of desingularization of the point of order 4, intersection of 4 leaves of 4 two-dimensional leaves in the 3 space. There is another version of such equation, which is called the permutahedron equation. So just to compare, the element S play the role of phi, but here there are additional element R. And this equation is illustrated by this picture. On both sides, we see the permutahedron of dimension 4. So it's a polyhedron with vertices in points which are obtained by the action of the group S4 on coordinates. So let us consider a point with coordinates 1, 2, 3, 4 in a 4-dimensional space, and its orbit with the action of the group S4. So it appears to be a polyhedron with faces which are of valency 4 and of valency 6. Okay, so it's a polyhedron P4, and there is equation which can be related with polyhedron, which is causally related to the previous one. Kapranov and Voevodsky interpret this equation as a family of the tetrahedron equation, but for me, I just like to simplify this condition. So if R, which is on rectangular faces, is trivial, it is just the tetrahedron. With the help of solutions of the tetrahedron equation, we appear to construct a variant of invariance of two nodes. Principally, principally, it is given by a partition function of the same flavor. But here, the coloring is a coloring of edges of the graph of singular point of a diagram of it. So in the construction of Cartan and Sayatan, the coloring was by element of a bundle of the two leaves of this diagram. So it is analogous to the fundamental group bundle associated to the fundamental group of the completion of this two. Here it is different construction. So it is a coloring of arcs of double points of a diagram of a two node. And this with this coloring, we construct a partition function, which is also a sum over the space of admissible coloring, the product of the triple points of some values, which are also take the role of homology classes of associated complexes with the solution of the tetrahedron equation. And our theorem with Igor Kiripanov and Georgy Sharigin states that this partition function is invariant with respect to all odd Rosman moves. And moreover, for some particular choices of cocycle, cocycle it is also invariant with respect to the 6 Rosman move. Let us return to the here is the list of Rosman moves. The 7 Rosman move, it is literally the tetrahedron. But there are many other conditions to partition function to be an invariant of it or not. Okay. Okay. Let us consider the very known category of tangles, just of one tangles. So they are represented by curves, which so it's just the coordinates between the discrete sets on lines like this. The composition is defined obviously, and one can introduce the category of oriented tangles. So on each line here, I introduce the sign, and the lines also will be equipped with orientations. And this category is the morphisms in this category are generated by such composition of lines. And here is the list of relations on morphism in this category. There is a notion of a Riemann-Hopf algebra, which is a Hopf algebra with additional elements. So there is an R matrix, so it's a quasi-triangular Hopf algebra with additional element U subject to such condition. Element U and element V given in definition of the Riemann-Hopf algebra. For example, the universal enveloping algebra SF2 is a Riemann-Hopf algebra with R matrix given by universal R matrix given by this expression, and the element V is given by an exponent of the Cartan element of this algebra. The following theorem of Reshetikhin-Turaev is in the core of the field of quantum invariance of nodes. So it says that a map defined by this way, it is a map from the category of oriented tangles to vector spaces. and it is constructed with the help of element of the definition of the Riemann-Hochfeld. So it says that this map is a functor from the category of oriented tangles to the perspective. And moreover, this functor is isotopy invariant. It means that it produces the isotopy invariance of links movements. And moreover, for the case of Riemann-Hoch algebra, which is quantum universal independent algebra of Z2, it is just the Jones polynomial. Let us recall some basic facts from the category theory. Let C be a small category and D a category. Then the set of functors from C to D is a category. Those objects are functors, and morphism are natural transformation between functors. Natural transformation is a known notion for this detail. I just to introduce the name for the category of braided sets. Objects are braided sets, and maps are morphisms, which I defined at the beginning of my talk. So it's some map which computes with braidings. Classification problem of braided set is related to the category of functors due to the natural functor from this category of functors from oriented tangle to set to the braiding set. So it's a tautology, but it's important due to the fact that it is really natural to consider the category of braided sets. Okay. The next step is a two category of two tangles. And the two category is the following data. There is a set of objects, set of morphisms, and set of two morphisms. For morphism, it is the relation between object and morphism are defined obviously, and the two morphism can be illustrated by a diagram like this. So it is some two arrow between one arrows, and there is two ways to compose these arrows, a horizontal and vertical one. And there is a notion of braided category. So it is a two category with additional morphisms, which introduce the braiding of tensor products of object of this category. And one asks for this morphism an additional relation. An additional relation, which is in fact a two morphism. R1 A1 A2B, it is a two morphism between two one morphisms. I'd like to recall definition of the quasi-triangular topology. So in fact, it's a little bit more abstract way to say what is the quasi-triangular algebra, which induces a solution of the Yang-Baxter equation, but a little bit more basic structure. So in a braided two category, there is a two morphisms, between conditions which are strictly fulfilled in quasi-triangular Hoch algebras. And moreover, it is necessary that such two morphisms satisfy some additional relation, and one of them is illustrated by the permutahedron P4. there is a theorem which principally says that there is a braided monoidal 2 category which is related with isotopy classes of 2 tangles in 4 dimensions. And I'd like to define a set X to be a 2 braided set or a local braided set if there is a family of maps R alpha from X2 to X2 and additional map phi from the third Cartesian product of the index set A, which satisfy such set of equations, and functors from the category of 2 tangles to sets produce 2 braided sets. So it's an analog of the statement relating the braided set with functors from the category of 1 tangles to vector space. And this category, the category of functors from 2 tangles to set, is subject to our future research. Thank you very much.
Yes.
Very simple question. I don't understand why you should take one set of modes and take another. Is similar to ambient and regulatory, or and for application for the monitor, we can take the second step.
No, finally, we cannot found a geometric interpretation of this subset. So it's a technical condition. We
just take it.
Yes, we prove the invariance with respect to this type. So we couldn't find some geometrical framing for of this subset of nodes. But so it's an open question.
More questions? Okay, there are questions that for break for coffee, tea, during this call, and we continue